August 1944, Luzon, the Philippines. The wreck sat half-submerged in mud, its olive-drab armor scarred by shrapnel and fire. Japanese engineers from the 4th Technical Research Group approached cautiously. Before them was a tank they had heard about only through intelligence reports, the American M4A1 Sherman. The vehicle had been knocked out near San Manuel, during a skirmish with elements of the 14th Area Army. Its crew was gone. Its hatches were fused shut by heat. Yet to the officers from the Army Armored Technical Research Department, Rikkigun Jidosha Jijutsu Kenkyusho, this was a prize beyond value. For years, Japan's tank program had operated in isolation. Their most common medium, the Type 97 Chiha, weighed just 15 tons, armed with a 57mm Type 97 gun. It had served adequately in China. But against the newer Allied machines appearing in the Pacific, especially the Sherman 75mm M3 gun and 51mm frontal armor, reports from the field were grim. Now, for the first time, Japan could study the enemy's technology directly. By October 1944, the tank's remains were shipped under heavy guard to Sagami Arsenal, 35 miles southwest of Tokyo. The facility, located near Sagamihara, was the center of Japan's armored vehicle development and testing. Engineers from the 1st Army Technical Bureau prepared a full teardown analysis: armor thickness, suspension geometry, gear ratios, and internal layout. The findings astonished them. The Sherman's cast hull, using homogeneous armor steel, provided uniform resistance with far fewer weak welds than Japan's riveted designs. Its Continental R975 radial engine, producing 400 horsepower, propelled the 30-ton vehicle to 24 miles per hour, 39 kilometers per hour. The Type 97, by contrast, carried a 170 horsepower Mitsubishi diesel, barely half the power for a vehicle half the weight. More revealing was the Sherman's transmission. The 5-speed synchromesh gearbox allowed smooth, high-speed shifts under load, a feature absent in Japanese models. Tests showed the Sherman could climb 60% gradients and cross 2.3-meter trenches. The Type 97 could barely manage 45% and 1.8 meters. Inside, the engineers documented the Euro stabilizer, an electromechanical system that kept the main gun roughly level even while the tank moved. The device was crude by post-war standards, a small spinning gyroscope linked to hydraulic servos, but it allowed American crews to fire on the move, something no Japanese vehicle could do. In a classified report dated November 2, 1944, Captain Masao Otsuka, lead mechanical examiner, wrote, "This vehicle demonstrates industrial capacity beyond our domestic reach. Its electrical system, transmission precision, and welded armor construction indicate a high level of mechanization. Even in damaged condition, its internal organization reflects efficiency of design unseen in our tanks." To confirm the Sherman's combat effectiveness, the research group compared ballistic data from captured Allied documents. The 75mm M3 gun fired a 6.8 kilogram shell at 690 meters per second, penetrating 78mm of armor at 500 meters. Japan's most powerful tank gun at the time, the Type 147mm, achieved just 55mm penetration under the same conditions. A second analysis tested Japanese ammunition against recovered Sherman armor plates. Using a Type 1 anti-tank gun, the results were bleak. At 100 meters, the rounds left shallow craters. None achieved perforation. Even more alarming was the tank's battlefield reliability. Reports from Guam and Saipan described Shermans completing 100-hour operations without mechanical failure. Type 97s often broke track pins or overheated after 20 hours. By December, the engineers had one conclusion: the Imperial Army's armored doctrine, built around speed, lightweight, and infantry support, was obsolete. The Sherman was not simply a bigger tank. It was an expression of industrial dominance. As one technician summarized in his December 18 notes, "Against this, our production and metallurgy are 10 years behind." The comparison marked a quiet turning point. Japan's engineers began drafting designs for a new generation of tanks, heavier, more powerful, and better protected. But time was running out. The Allies were advancing across the Pacific. And every island they took brought the Sherman closer to Japan's shores. January 1945, Sagami Arsenal, Kanagawa Prefecture. Snow lay thin across the proving ground as officers from the Army Armored Headquarters assembled inside a drafty concrete hangar. On a raised platform sat the dismantled remains of the American M4A1 Sherman, stripped, catalogued, and measured. Around it, Japanese engineers displayed blueprints for proposed countermeasures. Thicker armor, a longer gun, a new suspension. The meeting opened at 0900 hours. Colonel Kiyomi Watanabe, chief of the Army Armored Technical Bureau, summarized the problem. Our present doctrine assumes tank combat will be rare. Yet in the Philippines, Shermans appear in every engagement. Infantry-based defense will not suffice. For 2 decades, Imperial Japanese Army doctrine had viewed tanks as extensions of infantry, tools for breakthrough and exploitation, not duels with other tanks. The Type 89 Igo and Type 97 Chiha had been optimized for soft targets in China, not for armored warfare. Speed, range, and simplicity had outweighed protection and firepower. The Sherman forced a reckoning. In the weeks following the analysis, the Bureau initiated Project Chitu and Project Chiri, heavy tank programs already underway but now given priority status. Both designs traced back to 1943, but had stagnated due to steel shortages and factory bombings. The Type 4 Chitu, planned to weigh 30 tons, would mount a 75 mm Type 5 gun derived from the Type 88 anti-aircraft cannon, capable of penetrating 90 mm at 1,000 meters, finally matching Allied standards. The Type 5 Chiri, even larger at 37 tons, was intended to carry a 75 mm automatic loader and a 550 horsepower Kawasaki V12 engine. But the industrial gap loomed. Japan could not mass-produce heavy castings, nor supply the high-octane fuel the engines required. Testing of the Chitu prototype began February 1945, but it reached only 30 km per hour and suffered transmission failures after 12 hours. Engineers requested 3,000 kilograms of alloyed steel for further trials. Tokyo Arsenal could allocate only 400. By March, production priorities had shifted toward aircraft engines and suicide weapons. Meanwhile, field reports from Luzon and Iwo Jima confirmed the worst. On January 9, 1945, U.S. forces of the 6th Army landed at Lingayen Gulf with over 200 Shermans. The Japanese 2nd Tank Division, equipped mostly with Type 97s, counterattacked near De Mortis on January 17. At 0645 hours, 12 Type 97s engaged a column from the 716th Tank Battalion. Within 15 minutes, 9 Japanese tanks were destroyed by direct hits from 75 mm guns at ranges between 600 to 900 meters. The remaining vehicles withdrew, unable to penetrate the Sherman's frontal armor even at point-blank distance. The engagement was documented in a report to Imperial General Headquarters on January 24. Enemy armored vehicles sustained repeated hits from our Type 1 shells without disablement. Engines, suspensions, and turrets remain functional. Our vehicles ignite after the first return shot. That report reached Sagami within a week, confirming the engineers' laboratory conclusions with battlefield proof. Inside Japan, the Armored Bureau's response was methodical but desperate. Teams re-examined captured Shermans piece by piece. They tested domestic shells against its armor. They studied the Sherman's vertical volute suspension, its 12-volt electrical system, and its power-assisted turret traverse that could rotate 360 degrees in 15 seconds, 5 times faster than the manually cranked Type 97 turret. Every test ended the same way: Japanese hardware lagged. The Chiha's 57 mm gun, designed for infantry support, lacked both velocity and elevation control. Even the upgraded Shinhodo Chiha with its 47 mm high-velocity gun failed against the Sherman's Glassy. By March 1945, engineers concluded that only a high-velocity 75 mm or 88 mm weapon could defeat the M4 frontally, neither of which Japan could field in significant numbers. The contradictions ran deeper than technology. Japan's military structure divided innovation between the Army and Navy, each competing for dwindling resources. Steel allocations, rubber imports, and fuel shipments were cut in half after the fall of Burma in mid-1944. The Sagami engineers could design a rival tank on paper. They could not build one in numbers that mattered. As B-29s began striking the Tokyo-Yokohama industrial zone in February and March 1945, production lines for the Chitu and Chiri fell silent. The comparison with the Sherman had laid bare not just a tactical shortfall, but the end of Japan's capacity to compete in mechanized war. Yet the engineers persisted. Their next step was not to outgun the Sherman, but to understand why it worked, and whether Japan could adapt its lessons to defense. March 1945, Sagami Arsenal, Kanagawa Prefecture. The war was closing in. Allied bombers crossed Japan's skies daily. Yet inside the reinforced hangars of Sagami Arsenal, engineers continued their dissection of the Sherman tank. Power plants, optics and wiring looms were laid out on trestle tables. The objective had shifted, not to copy the enemy but to understand the system that produced him. Lieutenant Colonel Nobuharu Tanabe, head of mechanical evaluation, issued a directive on March 12, 1945. Every component is to be examined for manufacturing method, tolerances, and field serviceability. We must know how the Americans build for war. Teams from the 1st Army Technical Bureau began detailed metallurgical analysis. Using chemical titration, they measured carbon and manganese ratios in the Sherman's armor plates. The steel, U.S. Army Ordnance Specification 8630, contained nickel and molybdenum, metals Japan could scarcely obtain after the loss of maritime routes in 1943. The findings confirmed what field units had long suspected. The enemy's armor was not only thicker but far tougher. In the electrical lab, engineers dismantled the gyrostabilizer Mk4 and the Westinghouse turret traverse motor. Each component bore serial markings and standardized fittings, evidence of precision assembly line production. A single traverse motor could be swapped between tanks without adjustment, something impossible in Japanese vehicles, which required manual fitting of gears and bearings. When the stabilizer was powered with a 24-volt test rig, the team observed smooth, consistent gun leveling up to 10 degrees pitch change. Notes recorded on March 18 described it as a simple but effective mechanism improving firing accuracy by 30 to 40% while in motion. The conclusion was brutal. Japan's workshops lacked both the electrical infrastructure and machine tool accuracy to reproduce it. Parallel studies focused on American logistics. A captured TM-9-731A technical manual, recovered in the Philippines, described depot maintenance procedures, spare part inventories, and field repair intervals. Engineers translated and summarized key passages. The U.S. system emphasized interchangeability. Engines, bogie wheels, and even complete transmissions could be replaced within hours using mobile workshops. Japanese armored units, by contrast, operated with minimal spare parts and few recovery vehicles. A disabled tank was often abandoned or stripped in the field. The 1st Tank Division report from Luzon, February 1945, recorded that of 98 Type 97s, only 22 were lost to enemy fire, the rest failed mechanically or ran out of fuel. By April, the Sagami team compiled a classified report titled, Comparative Study of American Armored Force Maintenance Practices. Its key conclusion read, enemy operational endurance arises not solely from tank quality but from a system of repair, resupply, and replacement operating at levels beyond our capacity. The Sherman, they realized, was not exceptional as a single machine. It was exceptional because it could be replaced. Inside the design bureau, this insight reshaped Japan's final armored projects. The engineers concluded that a few heavy prototypes could never change the war's outcome. Instead, they proposed adapting existing designs for defensive ambush, concealing tanks in terrain, improving gun elevation, and developing new ammunition types. The Type 147mm Apache round was redesigned with a hardened steel core and improved fuse delay, raising penetration by 8 to 10 mm. The Type 475mm at gun, a derivative of the Type 88AA, entered limited production in May 1945, capable of defeating a Sherman side armor at 800 meters. Tests at Iruma Proving Ground, north of Tokyo, confirmed results on May 27. 3 penetrations out of 5 at 700 meters using tungsten-capped rounds. But tungsten stocks were nearly exhausted. By June 1945, the engineers' work had become an academic exercise. US B-29s flattened Kawasaki's tank factories. Rail shipments of armor plates stopped entirely. Still, Sagami Arsenal staff continued documentation. Hundreds of blueprints, cross-sections, and mechanical drawings of the Sherman systems. These files would later become the foundation of Japan's post-war industrial revival. The final internal memorandum, dated June 28, 1945, read simply, "The enemy's strength is in organization. We must learn that or we will never build again." The Japanese engineers had uncovered more than the secrets of a tank. They had glimpsed the power of an industrial nation mobilized for total war. June 1945, Sagami Arsenal, Kanagawa Prefecture. In a cordoned-off bay of the arsenal, beneath a sagging roof patched with tar paper, stood the prototype of Japan's most advanced tank, the Type 4 Chitu. Painted in crude camouflage and lacking its turret machine gun, the vehicle embodied 5 years of design evolution. It was also a symbol of futility. The tank weighed 30.8 tons with 75 mm of frontal armor sloped at 60 degrees. Its Type 5 75 mm gun, a 56 caliber weapon with a muzzle velocity of 850 meters per second, matched the ballistic performance of the American M4A3 76W's main armament. The engine, a Mitsubishi Type 4 V12, delivering 400 horsepower, could move the vehicle at 40 km per hour on level ground. On June 12, 1945, the Cheetah rolled out for its first mobility test along the Sagami test course. Observers from the Army Armored Headquarters and Technical Bureau watched in silence as the tank completed 3 laps, totaling 6.8 kilometers. The test concluded without major incident, a rare success in the collapsing Japanese war industry. But the victory was hollow. The prototype used hand-forged parts, many machined from salvaged steel. Its powertrain, adapted from a naval auxiliary engine, overheated after 40 minutes. With Allied bombers targeting foundries daily, there was no prospect of mass production. 2 weeks later, inside a nearby workshop, work continued on the heavier Type 5 Chiri, intended as Japan's answer to the Sherman and even the M26 Pershing then entering U.S. service. The Chiri was projected to weigh 37 tons, with a 75 mm Type 5 automatic loading cannon and a 550 horsepower Kawasaki V12. Engineers envisioned a range of 250 kilometers and a top speed of 45 kilometers per hour. But the war's realities intruded. On June 19, 1945, a B-29 raid on the Kawasaki aircraft plant in Akashi destroyed the engine assembly line. Blueprints, test jigs and tooling were lost. When Colonel Watanabe reviewed the situation on June 25, he wrote, "Without engines or armor plate, these projects cannot proceed. Completion will be symbolic only." Still, the Army ordered that at least one Chiri hull be finished for morale and for study. By July 10, the half-completed vehicle sat in a Sagami workshop, turretless, unarmed, a steel shell representing Japan's final attempt to bridge the technological divide. In contrast, American industry was producing at unprecedented scale. By mid-1945, U.S. factories had delivered 49,234 Shermans, along with more than 6,000 variants including the M10 and M36 tank destroyers. Replacement tanks arrived in the Pacific faster than Japanese forces could destroy them. Japanese intelligence intercepts from July 1945 reported that U.S. 20th Armored Group in Okinawa had landed with 280 Shermans, more tanks than Japan had operational in the entire home islands. The comparison was staggering. Even if the Cheetah had entered production at 1 unit per week, Japan would have needed a century to match American output. Testing continued despite futility. On July 15, the Cheetah's gun team fired 10 rounds at a decommissioned Type 97 hull from 1,000 meters. All penetrated cleanly. The engineers noted dispersion within 0.45 mils, a remarkable result for a weapon assembled under bombardment. 2 days later, the arsenal's electricity failed during a B-29 raid on Yokohama. The next morning, the testing field was cratered. The Cheetah lay covered in debris but intact. When the arsenal's director, Major Kenji Ikeda, inspected it, he ordered it preserved for future study. That decision would prove prophetic. When Japan surrendered on August 15, 1945, Sagami Arsenal held the only 2 advanced tanks in existence, the Cheetah prototype and the unfinished Chiri hull. Both were seized by U.S. occupation forces in September and shipped to the Aberdeen Proving Ground in Maryland for evaluation. American engineers documented their construction, noting solid design principles constrained by primitive manufacturing. In a confidential 1946 report, Aberdeen engineers summarized, "The Type 4 Cheetah, had it been produced in quantity, could have equaled the early M4 series. Its limitation was not concept but capacity. The countermeasure had arrived too late to matter. Japan's engineers had achieved technical parity on paper, but they had lost the industrial war years earlier. The lessons from Sagami would not end there. In the ashes of defeat, the same engineers would be called upon to rebuild, and their understanding of the Sherman would shape the next era of Japanese industry." September 1945, Sagami Arsenal, Kanagawa Prefecture. When American troops of the 8th Army entered the arsenal complex on September 4, 1945, they found the wreckage of a vanished industry. Roofs caved in from bombing. Assembly lines frozen mid-production. Inside one cavernous hall, half buried under dust and shrapnel, stood 2 hulks, a completed Type 4 Cheetah and beside it the unfinished hull of a Type 5 Chiri. Captain Earl S. Morrison, U.S. Ordnance Corps, recorded the discovery in his field log. 2 tanks of unusual design. Modern appearance. Workmanship inconsistent, strong structure, crude details. Recommend recovery for technical evaluation. Within weeks, the U.S. Army Technical Intelligence teams cataloged the find under Project Number 264. By October 10, both tanks had been crated and shipped aboard the transport General H.W. Butner to Yokohama Port, then onward to Aberdeen Proving Ground, Maryland. The occupation had begun not only as military control, but as a forensic examination of Japan's technology. At Aberdeen, engineers stripped the Chitu to its frame. Each plate, weld, and casting was measured against American standards. Metallurgical tests revealed medium hard-rolled steel, carbon content 0.35%, hardness 235 Brinell, comparable to early US M3 and M4 armor. But the steel's grain structure showed impurities from low-temperature rolling and inconsistent heat treatment. The gun impressed American analysts. The Type 575mm with a muzzle velocity of 850 meters per second, fired a 6.6 kilograms AP shell that could penetrate 90 millimeters of armor at 1,000 meters, nearly identical to the US M176mm. Firing tests at Aberdeen in March 1946 confirmed stable ballistics and good accuracy. Yet the automatic loading system of the Chiri was incomplete, and the breech mechanism showed machining marks 10 times rougher than US tolerance norms. Aberdeen's summary report, dated May 5, 1946, concluded, "Design indicates sound theoretical understanding but poor metallurgical control and inadequate production precision. Overall concept compares favorably to 1943 US models." The engineers also noted several features clearly influenced by observation of Allied tanks: welded hull seams, sloped armor, large turret ring diameters, and even the adoption of a commander's cupola similar to the Sherman's late war design. Back in Japan, the Supreme Commander for the Allied Powers, SCAP, began cataloging surviving military factories. Sagami Arsenal was renamed the Tokyo First Army Depot, its machine tools inventoried for peacetime use. American ordnance officers interviewed surviving engineers, including Colonel Kiyomi Watanabe and Lieutenant Colonel Tanabe, both of whom had led tank development since 1943. Their testimonies formed part of the U.S. Army Technical Intelligence Report 16-45, titled Japanese Tank Development and Production Methods. The report, completed in December 1946, emphasized how Japan's doctrine and resource constraints had dictated design priorities. The Japanese tank arm, initially patterned on French concepts of infantry support, did not evolve for tank-versus-tank combat until exposed to U.S. material. Industrial limitations prevented the realization of advanced designs already conceptually sound. The Americans concluded that the Imperial Army's technical brain trust, though defeated, held substantial theoretical competence. Under SCAP's supervision, many of these same engineers were quietly reassigned to civilian industries: automobile plants, construction machinery, and later, electronics. Between 1946 and 1950, Sagami Arsenal transformed. Its surviving lathes and forges were repurposed for agricultural equipment and trucks. Mitsubishi and Kawasaki, once prime military contractors, redirected their metallurgical and precision engineering expertise into the civilian economy. The lessons of the Sherman analysis had not been forgotten. Uniform production standards, modular design, and reliability over complexity became guiding principles of Japan's reborn industry. In 1949, as the National Police Reserve, forerunner of the Japan Ground Self-Defense Force, formed under American guidance, Japanese engineers were again called upon, this time to maintain imported M4A3E8 Shermans provided by the U.S. under the Mutual Security Program. For the men who had once dissected a burned-out Sherman in Luzon, the irony was complete. A decade earlier they had studied the tank as a symbol of defeat. Now they maintained it as an Allies machine, the same vehicle that had shown them the meaning of modern industry. The occupation had exposed Japan's limitations, but it also planted the seed of its resurgence. The same analytical rigor that once measured foreign armor thickness now measured engine tolerances for trucks, ships, and eventually automobiles. The Sherman had been more than a weapon. It had been a blueprint for how to build, predictably, efficiently, and in scale. The engineers who survived Sagami would carry that lesson into a new era, one where production, not destruction, defined power. 1947, Sagami Arsenal, now the Tokyo First Army Depot. The war's debris had been cleared, but the machines remained: rusted presses, lathes, and milling tables once used to forge armor plates. American occupation authorities now ordered them converted for civilian production. Under the supervision of GHQ Economic and Scientific Section, former Imperial Army engineers were reassigned to rebuild Japan's mechanical industry from the same foundations that had produced tanks and guns. The change was immediate and profound. Lieutenant Colonel Nobuharu Tanabe, once head of mechanical testing for the Type 4 Chitu, became chief technical advisor at Komatsu Iron Works in Ishikawa Prefecture. The company, which had built artillery tractors during the war, was repurposed to manufacture bulldozers and road graders for Allied reconstruction projects. Its first post-war model, the Komatsu G40, was based directly on the tracked suspension layout of the Type 97 tank. At Mitsubishi Heavy Industries, demilitarization orders forced a split into separate regional firms: Mitsubishi Nagasaki, Mitsubishi Kobe, and Mitsubishi Tokyo. Yet engineers who had drawn blueprints for tank engines now found themselves designing diesel generators, marine engines, and eventually small automobiles. They retained the habits of precision documentation and standardized assembly learned from dissecting the Sherman 2 years earlier. By 1948, Japan's machine tool capacity had recovered to 40% of its 1941 level, but output was far more efficient. Standardized jigs, gauges, and calibration procedures, all modeled after U.S. ordnance standards observed during the occupation, became the new industrial doctrine. The goal was no longer battlefield parity but production repeatability. Former Army metallurgists from Sagami led studies on heat treatment and carbon control, referencing the U.S. Army Ordnance Specification 8630, the same steel used in the Sherman's hull. From this emerged Japan's first post-war standard alloy classifications, precursors to the JIS Japanese Industrial Standards system established officially in 1949. Where once armor plates were rolled inconsistently by hand, factories now adopted temperature-controlled furnaces and timed quenching cycles. Scrap from decommissioned tanks was melted down and recast into farm implements and bridge girders. Each improvement was documented, measured, and standardized, a direct cultural legacy of the wartime research method. In 1950, the Korean War erupted. Japan, still under occupation, became the logistics hub for U.S. forces. The sudden demand for trucks, heavy machinery, and spare parts accelerated industrial rearmament. Companies like Komatsu, Hitachi, and Mitsubishi received American contracts to produce engines, compressors, and construction vehicles. Many of these designs reused technical drawings archived at Sagami. The U.S. Army requisitioned Japanese workshops to maintain M4 Shermans and M26 Pershings transiting to Korea. Among the technicians were men who had once tested Japanese guns against Sherman armor. Now they inspected the same vehicles for alignment, suspension wear, and gear backlash, all procedures they had documented in 1944. The Tokyo First Army Depot became the National Research Institute for Defense Technology in 1952, as Japan regained sovereignty. The archives from Sagami, containing over 8,000 pages of pre-war and wartime tank design data, were cataloged and preserved. These blueprints, once classified military secrets, became engineering references used by universities and industry alike. By the mid-1950s, the transition was complete. Japan no longer built tanks, but it had mastered the principles that once defined them: tolerance control, production flow, and systems integration. The intellectual descendants of the Type 97 engineers now applied those lessons to trucks, cranes, and industrial vehicles. Komatsu's 1953 crawler tractor used a bogie suspension modeled directly on the Sherman's vertical volute system. Mitsubishi's diesel engines borrowed combustion chamber geometry from the Cheetah's V12. Precision bearing manufacturers like NSK adopted interchangeability standards identical to those documented in the American Technical Manual TM9-731A. When Japan joined the United Nations in 1956, its exports included power shovels, lathes, and compact diesel trucks, the peaceful counterparts of machines once designed for war. Each bore the invisible lineage of Sagami Arsenal's engineers, who had turned defeat into discipline. The Sherman had been dismantled to reveal its secrets of power. A decade later, those secrets had been rewritten as the blueprints of a nation's rebirth, one measured not in armor thickness or muzzle velocity, but in precision, efficiency, and endurance. 1954, Camp Takayama, Kanagawa Prefecture. The rising sun flag no longer flew over Sagami Arsenal, yet armored tracks once again rolled across its proving ground. This time they bore the White Star of the United States. Rows of M4A3E8 EZ-8 Shermans, freshly refurbished in Japan, idled beside American advisors from the U.S. Army Military Assistance Advisory Group, MAG. Standing among them were Japanese technicians, veterans of Sagame's Wartime Research Bureau, now wearing the insignia of a new organization, the Japan Ground Self-Defense Force (JGSDF). On July 1, 1954, the JGSDF was officially established. Its first armored regiment, equipped with surplus M4 Athreus and M24 Chafees, formed at Camp Kamikado. For the men who had once measured the Sherman's armor with calipers under wartime secrecy, the sight carried a strange symmetry. The tank that had exposed their defeat now served as their teacher. Under the U.S.-Japan Mutual Security Assistance Program, Japan received 389 M4 Athreus and 50 M24 light tanks between 1954 and 1957. American instructors conducted gunnery and maintenance courses at Sagami, now renamed JGSDF Ordnance Training School. The curriculum was familiar: systemized maintenance intervals, part interchangeability, and field repair standards identical to those the Japanese had studied in the captured technical manuals a decade earlier. Former Imperial Army Engineer Captain Ret. Masao Otsuka, the man who had written the 1944 report comparing the Type 97 to the Sherman, returned to service as a civilian consultant. In an internal memorandum dated October 5, 1955, he wrote, "We once dissected this tank as an enemy artifact. Now we rebuild it under instruction. The lessons remain the same: precision, reliability, repeatability." American military planners soon encouraged Japan to begin developing its own modern tank to replace the aging Shermans. The goal was a lighter vehicle suited to Japan's mountainous terrain and limited infrastructure, but with the firepower of contemporary Western designs. The result was Project STA, Special Tank, Japan. Initiated in 1955 by the Technical Research and Development Institute, TRDI, the direct descendant of the old Army Technical Bureau. The project's leadership drew heavily from Sagami alumni. Chief Engineer Shigeo Otaka, who had once worked on the Chiri suspension, adapted lessons from both the Sherman and post-war American designs. The SDA's torsion bar suspension derived from the M24 and M26, but its compact hull and sloped armor reflected pre-war Japanese efficiency. Prototypes SDA-1 and SDA-2, completed in 1956, weighed 34 tons and were powered by a 570 horsepower Mitsubishi Type 12 HM21 V12 diesel, a refined descendant of the Cheetah engine concept. They mounted a 90mm gun, the same caliber as the US M48 Patton. During testing at Sagami, the SD-2 achieved 45 km per hour and demonstrated stable gunnery using an electric turret traverse nearly identical in function to the Sherman's Westinghouse motor. American observers, including Colonel Eugene Salet of MAAG, noted in a 1957 report, "Japanese design displays remarkable assimilation of U.S. production philosophy. Emphasis on reliability over complexity is consistent with lessons drawn from Allied armor during the war." That philosophy culminated in 1960 with the adoption of Japan's first post-war indigenous tank, the Type 61. It embodied everything Sagami's wartime engineers had lacked: standardized parts, interchangeable subassemblies, and a manufacturing system capable of series production. The Type 61 was not revolutionary, but it was reproducible, the exact quality Japan had envied in the Sherman. By the early 1960s, the JGSDF maintained a mixed armored fleet. American M4 Athreus and M24s gradually replaced by domestic Type 61s. Each Japanese vehicle carried a lineage traceable through defeat, study, and adaptation. The shadow of the Sherman was not the vehicle itself, but the production ethos it represented, a discipline of precision and logistics that became Japan's industrial backbone. In the words of engineer Kenji Ikeda, recorded in a 1962 NHK interview, "The Sherman showed us that victory belongs to the factory before the battlefield. We learned too late, but we learned completely." 1964, Sagami Proving Ground, Kanagawa Prefecture. The Type 61 tank rumbled across the same test track where, 20 years earlier, Japanese engineers had dismantled a burned-out Sherman under wartime secrecy. Its diesel engine roared clean and steady. Its 90mm gun stabilized smoothly over uneven ground. Watching from the control tower, a few gray-haired men recognized every curve of the course. Veterans of the old Army Armored Technical Bureau, now senior advisors in Japan's reborn defense industry. For them, the circle was complete. The lessons learned from a single captured tank had matured into a national doctrine, not of conquest but of precision engineering. In post-war Japan, tanks became rare symbols. Industry became the battlefield. The same principles that defined the Sherman's dominance, mass production, modularity, interchangeability, had migrated into factories, shipyards, and assembly lines across the country. By the mid-1960s, Mitsubishi Heavy Industries and Komatsu Limited had become the twin pillars of Japan's mechanized output. Their diesel engines powered trucks, ships, and industrial generators exported worldwide. Engineers trained under U.S. Ordnance Systems introduced statistical process control, first applied to tank tolerances, now governing every automobile component. At Nagoya Works, former tank metallurgists oversaw precision heat-treating furnaces that operated at plus or minus 5 degrees Celsius accuracy, a margin unheard of in 1944. That fidelity produced crankshafts that lasted twice as long as American equivalents. Toyota and Nissan adopted the same methods. Japan's car exports would soon eclipse the nation's pre-war steel output entirely. Within the Japan Ground Self-Defense Force, the Type 61 successors embodied the same pragmatic evolution that once defined the Sherman. The Type 74, 1975, introduced hydropneumatic suspension and advanced fire control, yet weighed only 38 tons, light enough for Japan's bridges, precise enough for its doctrine. The Type 90, 1990, would carry that lineage further, integrating a 120 mm rainmetal pattern smoothbore built under license but refined with domestic steel and electronics. Each generation shared a design DNA that traced back to two machines studied at Sagami in 1944. One Japanese, one American. The Type 97 Chiha's compact efficiency met the Sherman's production philosophy, yielding a uniquely Japanese balance of craftsmanship and standardization. Declassified U.S. Ordnance evaluations from 1967, reviewing 2 decades of Japan's industrial cooperation, concluded, the Japanese armament industry, once limited by material scarcity and decentralized methods, has adopted American production discipline to an exceptional degree. The influence of World War II technical intelligence exchange is direct and measurable. That transformation extended far beyond tanks. Japan's heavy industry firms evolved into global suppliers of construction vehicles, mining equipment, and precision engines. The Komatsu D50A, introduced in 1965, borrowed track geometry almost identical to the Sherman's VVSS suspension, now moving earth instead of men. Even the testing culture survived. The meticulous data sheets, the calibration of torque values, the insistence on measurable repeatability, all stemmed from the 1944 disassembly of that captured M4A1. What had begun as reverse engineering became a national mindset. Every product could be improved through analysis, iteration, and documentation. By the 1980s, few of the original Sagami engineers remained alive. Yet the factories they helped shape continued to embody their discipline. Japan's industrial miracle, its cars, electronics, and precision tools, stood on foundations laid by men who once measured enemy armor thickness with hand gauges under flickering lamps. The Sherman had been, unknowingly, their greatest teacher. Its legacy was not in its gun or armor, but in its system, the unity of design, logistics, and industry that Japan absorbed and made its own. On the proving ground at Sagami, the Type 61's engine idled down, and the sound of its tracks faded into silence. In that quiet, one could trace an unbroken line, from the scorched fields of Luzon, August 1944, to the precision factories of a rebuilt nation. The contest between the Type 97 Chiha and the M4 Sherman had ended in defeat. But from that defeat, Japan had forged something far more enduring. A mastery of steel, born from the study of loss, and perfected in the pursuit of precision.